Bismillahirrahmanirrahim. So today's lecture is about the concept of distributions. What are distributions? Let's see. So actually there is a lot of background required, but you have already had this background, so that's very useful. Models and reality are different things. Basically, there is the observable, which we see, those are the numbers. Then there is the model, which is there is the reality which is hidden. The hidden reality produces the observations, and a model is an attempt to capture some aspect of that reality. There are three different things. The reality produces observations, and we have a model. Model is our guess about what the reality might be like. So today's lecture will focus on two central concepts. What is a distribution and what is an IID sequence. IID means independent and identically distributed sequence of random variables. Both of these are unobservables. Both of these are actually models. So these are mental constructs. These are ideas in our mind. So to understand them, we have to understand mental structures. So now observations, we see observations, rainfall over here, somebody's, different kinds of random events are taking place. And we say, can we think of this as a random variable? So the question of whether we can think of this as a random variable is different from the question of whether this is actually a random variable. And these two concepts are confused because very frequently people confuse the model with the reality. So when I flip a coin, the question, is this outcome a random variable? This is the wrong question. The right question is, can we model this as a random variable? So now a random variable is something which is purely a mental construct. It has no reflection in reality. So random variables are important, and random variables come from distributions. So there are two levels of hidden reality. We can never see what a distribution is. It is not an observable concept, and we cannot see random variables. So these things have to be modeled in our mind. So we have to have clarity of thinking in order to understand what is going on here. Okay, so observations are there: rainfall, crop yield, grades, GNP, weight. Are this random variable? That's not a relevant question, not a useful question. Would it be useful to model it as a random variable? Well, that depends on what you're going to use it for. So until you have a issue, until you have a problem that you're trying to solve, you cannot ask the question, is this a random variable or is it not? Because the question by itself does not make sense. In fact, you can say that all models are false. Then if you say, is this a random variable? You can say no. So just like, to explain it very simply, consider the concept of number 3. So what is 3? There is no existence of this in this real world, because 3 is an abstraction. It's a concept. You can say, these are 3 bottles, and these are 3 students, and those are 3 cows. But 3, show me the 3 in the real world. There is no 3 in the real world, because 3 is an abstraction. It's a concept which exists in our minds only. Doesn't exist in the real world. Just like that, random variables are a concept which exists in our mind. It doesn't have any counterpart in the real world. So sometimes it's useful to think of this. But to understand random variables, to understand distributions, we have to exercise our brains, because it's not something like understanding that this is a door, because that's out there and we can understand it by our experience. But when you want to understand random variables, then you have to exercise your mind muscles, because it's only within the mind that you can construct random variables. Alright, so the most useful, the most clean, easy to understand, easy to see example of random variables comes from random sampling. So I've picked up one example like this. This is a recent poll from Gallup organization in Pakistan. What they did is they take a random sample of 2,000 taken from the entire population of Pakistan. And remember, the property of a random sample is that everyone should have an equal chance to be included in this sample. So that is what. So how do you do that? It's very difficult. For example, suppose I want to take a random sample of one student from this class, then I could do that by listing all the names and then selecting a random number which is equally likely to be any one of the 15 students here, and then selecting that numbered student. But it's not I cannot select a random student just by closing my eyes and waving my hand and saying, oh, this is a random choice, because not everyone will have an equal chance. I need to ensure everyone has an equal chance. So after you used a random sample, then you looked at what happened in this random sample and you say that, okay, 64% of people said yes to the question of, is the eradication of interest possible? 30% said no, it cannot be eradicated. And 6% said maybe, we don't know. Don't know or no answer, no response. So this is the current situation. So this, in the sample, this was the proportion. But now the Gallup poll is saying, okay, this is the proportion in Pakistan. How do you know? You only saw 2,000 people and there are crores of people in Pakistan. So it seems very silly. Suppose that I was to take this class and I would ask, Acha, let's do that. So raise your hand if you think that eradication of interest is possible. Yes? Raise your hand. एक आदमी या दो आदमी तीन आदमी. So there are 3 students in this classroom who think that eradication is possible, and 3 out of 5, 10, 13. So the proportion in this class is 3 out of 13. So can I conclude from this that in Pakistan about 3 out of 13 people will think that eradication of interest is possible? The answer is definitely no, because this class is not a random sample from Pakistan. So how can you say, as Gallup is saying, that 64% of the Pakistanis believe that eradication is possible? They never went and talked to all of Pakistan. This is because the random sample was chosen in a certain way, which we have discussed actually. And if we model this random variable as a theoretical random variable and we do the calculations for the model, then from that we could come to some conclusion about what is happening in all of Pakistan. And so this model is used to come to a conclusion. Now, is this a useful model? Well, if we go and we explore, we can try to find out what will happen in all of Pakistan. And if it is within the error bounds, then we would say, yes, this is useful. If we went and took a survey of all of Pakistan and we found out that only 30% of people believe this, then we would say this model is not useful. And actually this kind of thing gets done because Gallup in the USA takes a poll of 3,000 Americans and predicts the elections. And then the elections actually take place, and usually, so the whole population is doing this, and usually the numbers are fairly close, but also the numbers are not exactly within close to the extent that the model predicts. And the model predicts that the number, the vote will be 64% plus or minus 2%, and sometimes the actual number is 4% different from. So the model prediction is not quite correct, but it is usually not disastrously off. In some cases, polls have been disastrously off also. So it means that this idea of random variables, where random choice is made from population, is fairly useful. It seems to be a roughly accurate way of thinking about the world, so we proceed with this. Okay, so suppose we have a population of 1 million people, and random choice is to choose one person from this population in such a way that all people have an equal chance of being selected. Now this itself is automatically unobservable, unprovable. This is a statement which we can never prove. Okay, we say, okay, in an alternate reality, somebody else would have been selected. And if we do this many times, we will eventually choose everyone. We will never know, because this was just one choice at one time. And a very famous example is the Vietnam lottery, in which what they did was they selected they put in 365 days of the month, days of the year, and they put the little balls with each day, and then they rolled them up, and then they picked them up at random, and the date that was selected first had the highest priority of being called for the Vietnam War lottery, and then the second one had the second priority, and so on. So if you were low on this lottery, then your chances of being called for being drafted into the army were low. So there was a big stakes game, life or death. Now it turned out that this choice was not random later on, in the sense that the procedure was supposed to guarantee that all dates have equal probability, but actually some dates received biased treatment. Some were more chosen more often. Basically, it was because the balls were not shuffled adequately, and so there was a lot of fuss about this. So it is impossible to know or prove or verify that everybody has an equal chance, because it's never observed. You only observe one choice. You don't observe all the possible choices that could have been made. So this is something which exists in our mind. This is like a concept of fairness. Was this lottery done fairly? Did everyone have an equal chance? This is something which is purely mental, because ultimately only one person will be chosen. जैसे कि teams में होता है, if you select, you toss a coin, and which team is going to bat first is chosen. So this is considered fair because we think that both teams have an equal chance of being chosen. But this fairness is because we think that the coin being tossed is equally likely to come up heads or tails. If somebody's put in a fake coin with both heads on both sides, then we would say it's not fair. So, all right. So I think that I'm trying to make a point about the model reality distinction, because this is not made in your conventional textbooks. Nobody understands this, nobody explains this. Alright, so let's suppose that we have a population of 1 million and I pick a person at random from this, and I'm trying to give the concept of the distribution. So in this case, distribution is the distribution of ages in the population. Suppose the person is chosen, and then any characteristic of this person will be a random variable. So let's think about age, very simple. What was the age of this person? So let's suppose that this population is all children from 0 to 5. So just to simplify, make my table short. So in the age range of 0 months to 12 months, less than 1 year, you have 500 children. And then in 1 to 2 category, you have 400 children, and 2 to 3. This is the population from which you are drawing a random sample. Then in 3 to 4, you have 200, and 4 plus you have 100. Okay, so the total number of children is 1500. From this, you choose one child at random, and then you look at the age. So the child chosen, the age of the random child chosen is the random variable. and the distribution of that random variable is the set of all possibilities, which is exactly this, which is in the background population. So the distribution of the age, if we make it an integer, is that 0 has the probability of 500 over 1/3, 1 has the probability, 4 over 15, 2 has the probability. So this is the distribution of this random variable. Suppose I took the age as a day, then the distribution would be accordingly, yani what is the probability of all the days within the population. Suppose I took it as the hour, then or time or exact time, then the distribution would now be the continuous density function, which we will actually be looking at. So this is to explain what is a random variable and what is a distribution in an intuitive, easy to understand way. So now, suppose I take a single random draw. What can I say about this? Yani technically, anybody can come up. So in this previous example, I choose a child at random. What can I say about it? At first it seems like there is nothing you can say, because the child will be 0 or 1 or 2 or 3 or 4. And so if I say to somebody that I have made a random draw from this population and the child's age will be either 0 or 1 or 2 or 3 or 4, he will say that you're not telling me anything new. This I knew in advance. So is there something that the concept that we have chosen the person at random with equal choices to all, and this is there something more that we can say about this? So this is when we start to use the model. I want to be able to say something. Okay, I want to tell you that if you pick a child at random from this population, XYZ will happen. So this is using the model. So what is this XYZ? Is there anything I can say? Well, look at the category of 4 plus. So that's only 100 children in that. So if you look at 100 over 1500, that's 1 over 15. The probability is 0.066, 6.6%. So that's a low probability event. So I could say cautiously that if you pick a child, the chances are that he will not be 4 years old. Okay? So then I have a 93.4% probability that I will be right. Right? 93? Yeah. So, one important thing is that if you want to make statements which are 100% certain, probability will never give you anything. Well, yeah, it will never give you anything useful. So, when we talk about probabilities, we are talking about things which will be true with high probability. That's all you can do. Have some confidence. And so there is something called the confidence level. So we can say confidence level. So this is just at what confidence? Now, ideally what we would like to do is to make certain statements which are true 100%. You cannot do that. So now there are conventional confidence levels like, okay, this statement is true with 99% probability. So that's a high level of confidence. It will be true, if you do this experiment 100 times, then 99 times it should be true and once it should be false. This is under the assumption that your model is perfect, which it will not be. So when you use your model and you make statements and your model turns out to be about 99 times you are right, then you can say the model is useful. So here in exactly this particular situation, suppose I draw a child at random and suppose that 90% of the time the child is not 4 years old, then I can say, look, the model is useful. It is making a prediction which is approximately true. So here we cannot use the conventional probabilities because there are no 5% statements and no 1% statements, but 6.6%. So suppose that in this model exactly, and we are doing the same thing, 1500 children, I draw, and the first time I draw, I get a 4-year-old. Then I make another random draw, I get another 4-year-old. I say something is wrong. this model is not working, it's not useful. There are two things which could be wrong. Maybe I don't have the right understanding of the population. Maybe there are not 100 but 500 children with age 4. I don't know, I got the wrong distribution. Or maybe my random sampling procedure is wrong. I am choosing children with a procedure that I thought is giving everybody an equal chance, but somehow or the other it's biased towards giving 4-year-olds a bigger chance. For example, suppose I say that, okay, everybody line up in the race and you race towards the end line, and the first one to come in will be the person that I will choose. So offhand it looks like random, everybody has an equal chance to succeed, but obviously the 4-year-old will win this race, so that's going to be a biased random procedure. But I might think that it is not random, I might think that it's random. Alright, so here are some pictures of the age distribution, male and female, in different countries. If you look at this one over here, this is the world. The world is fairly nice. You have young people at the bottom, and then it starts narrowing out at the top. So this is how you expect, lots of young people, and then as age proceeds, the more and more people drop out because they die. So ultimately at the high ages you get very few people. So this is what one expects. But if you look at Japan, this is the top, you see a very strange kind of, young people are very few, and in the middle, about between 40 and about 80, you have a lot of people, and above 80 you have few. So here is a society which is becoming very rapidly aging. Why did this happen? Well, there are many reasons. Well, suppose you start out with this is something which is called a demographic transition. As the income of a country increases and people become wealthy, they start having fewer children. For one reason, there are many reasons, but one of them is that people use children as life insurance policies, and once you are well off, you don't need that much life insurance. Also, when mortality of children decreases, when infant mortality goes down, then people have a lot of children because they know that many of them are going to die. So if they are not going to die, then you don't need that many children. So initially you start out with a process where there are lots of children, but as you go up as time progresses and wealth increases, you have fewer children. So ultimately your young children are few, and meanwhile the life expectancy has been increasing, so your older population becomes heavier. You look at the United States, it is fairly flat up to the age of 60, and then it starts shrinking according to age. In Ireland, you have a strange situation where there is a peak in the middle. Now this could correspond to some sort of a disaster, some catastrophe, some war, or some famine, something which took away a chunk of the population at a certain age, a certain amount of time ago. I think there was the Civil War and people left the country. And this is about 25 years ago this happened. If you look at Germany, oh yeah, the bottom, the green and red, the one with the different colors, that's New Zealand. That's something, I couldn't find the picture for Pakistan, but that's something like what we would see in Pakistan, that the young people, there's a lot of them, and then the population is much thinner at the top. Pakistan is like that, exactly. Germany has a Japan-like situation where young people are few, and so basically for this reason they are actually encouraging immigration. Turkish people coming in, Somali, because they need people to work. Everybody is very old, and they don't want to. If people are old and rich, they don't want to go and clean the streets, and so the many jobs are do not have workers, so they are having a favorable policy to immigration. But I wouldn't want to go into the countries. What I wanted to show is these are distributions that we see. This is the age distribution in different countries. If I draw a person at random from Japan, he is likely to be older. If I draw a person at random from New Zealand, he is likely to be younger. So this picture is the distribution, and then the random variable is one person that I draw from this. I'm trying to make the concepts clear. Alright, now here we have a set of scores on a SAT exam. This is artificial names and artificial scores. So, in my time, the SAT scores went from 200 to 800. I understand that the scores are different now, but I'm just using my own. So, Fazaldeen got 722 and Shazia Badr got 366. And then Maryam Bashir got 569 and so on. So now, these are people and they took a test and they got a score. Is there any way that we can model this as random numbers? It's not clear that we can do that or not. Is there any use that we can, of course, we can always assume that this is a set of random numbers, but that assumption is not very useful unless we are going to use it for something. So there are many ways that we could use. For example, we could say that, okay, these scores represent the scores that the population would get if they took the test. So then we can say, okay, the average score of people in Pakistan would be whatever the average here is. This would be valid if these people were randomly selected from the population. Typically, they will not be randomly selected. So then we get something like, okay, we can work backwards. Okay, look at these people. What is the population which they represent? And then we can maybe hope that this conclusion would be applicable to that population. So, for example, if I take these students and I get some idea about this is the score that these students have, then I could say that maybe this would be typical of students who are in MPhil programs in Islamabad. So there I would be on slightly better ground. It's not a random selection anyway, but you are more likely to be representative of this population. So I have a better chance that my model might work. Generally speaking, if you have something which is called a sample of convenience, and this is what it is. If I take this as my sample and I pretend it is a random sample, this is a sample of convenience. Generally speaking, the samples of convenience can be extremely bad, completely unreliable. So I can make an inference about Islamabad and it can be completely wrong. So, if somehow I have a situation which is close to a random draw, if somehow the students are picked at random, then the chances of my model working better are much better. So, in this lecture, our focus is on two concepts. One is the concept of a distribution, which I have explained, and the other is the concept of a sequence of random draws. And these two things are closely related to each other. If you know the distribution, then you will be able to say some very powerful things about the sequence of random draws. These random draws from the population are called IID. I means, the first I stands for independent. Each random draw should be independent. There should not be no relation. And suppose I pick the first draw as some person, and then the second draw is some relative of that person. Then the second draw will not be independent of the first draw, and that's then I will not be able to say anything about the population if I fail the independence. The second ID stands for identical distribution, means that the population should remain the same from draw to draw. Suppose I draw my first person from MPhil students of Islamabad, and the second I draw from MPhil students in Sialkot, then the population has changed, so these are not identical distributions. So these are the two concepts, and I want to explain further. Okay, so I've already explained that a distribution, see, if you have a parent population, it has some distribution. If I take that distribution is usually unknown, like what is the age distribution in Pakistan. It's very, very difficult to find this out. Actually, the census that we just did will actually give us this information to some extent, to the extent that people know their ages. In a lot of rural areas, people don't really have a very good idea about their age. They respond to the questions, but their response can be quite wrong. And sometimes it's biased. Sometimes people give the wrong age because of some consideration, like the girls give the age to be younger. So these are biases which you can show. If you do the average calculation of ages and then you say that there's a significant difference between this group and that group, then you can say that it's possible that the group gave the wrong information. Anyway, the distribution itself is unknown. The sequence of IID draws reveals some information about that distribution. So every random variable that we pick comes from some distribution. So there are two questions that are basic questions of probability and statistics. The fundamental question of probability is that you know the distribution, how will the random variable behave from that? And the basic question of statistics is the opposite question. Here is my random sample, what is the distribution? So these are the two questions. All of probability and statistics is concerned with only these two questions. Given the population, what does the random variable do? That's the question of probability. And given the random variables that we see, what is the distribution? That's the question of statistics. Okay, so if we have an IID sequence, then there's a lot of things we can do. But if we have only just one random variable, then it seems initially that there's nothing we can say, because we are picking one person, everybody has an equal chance. So anything that exists in the population you can see. So as we have already said, at the first glance it seems like there is nothing useful that you can say. But actually there is something that we do say and we do use, and this is very important. There are some things which are called central values, and there are some things which are called tail values. So given any distribution, the extremes are called the tails and the central values are called central values. So if you use the conventional levels, which we have already discussed, then you can say, okay, take the central 99% of the distribution and take 0.5% at one tail and 0.5% at the other tail, and those we will call as unusual values. So now I can, you see, if I want to make a prediction, I can say that, okay, with 99% confidence I predict that the age will be within this 99% confidence interval. So I exclude 0.5% from the top and 0.5% from the bottom, and now I am saying something which is different from what anybody could say. Yani, you see, if I make 100% certain statement, then anybody can say that. So now it requires knowledge of probability and knowledge of validity of my model. If this statement is true, that means that my model is working. So that's 99%. Sometimes we go to the 95% confidence level, and in that case we exclude 2.5% from the bottom and 2.5% from the top. This is your basic mechanism which is used for hypothesis testing. We construct some null hypothesis, then we make a statement which is true with 95% probability, and if that statement is fulfilled, then we say the hypothesis is true. If the statement fails, we find something which is in these tails, then we say the hypothesis must be wrong. Even though the hypothesis may not be wrong, the model may be wrong, but at least that's one way we, just like we said that if we see a lot of people with age 4, then we say that there is something wrong with the null hypothesis, that the distribution is that and the random sample is that. All right, now we look at some hypothetical densities. Now this situation, these are different kinds of normal densities. Basically, in the early development of probability, the population was not known, so people made hypothetical distributions like this, the normal distribution, and assumed that the population had distribution. So for example, I can say that the distribution of ages in the population is normal. I can say that the average age is around 30, and actually it's younger in Pakistan, and the standard deviation is 2, and so and the distribution of ages in the population is normal with mean 30 and variance 4. So this is a hypothetical assumption about the population, which is, as we have seen from the age distribution, completely wrong, because the age distribution is nothing like normal. So in some populations, basically I don't know of any serious realistic examples where the population itself has a normal. By the way, there are two words, density and distribution. Density is just it's different from distribution, but when you have a continuous random variable, we talk about the density. So these are different types of theoretical densities. So I can make a model. The true population, suppose that I don't know anything about what the true population is. I am taking a random sample. And now I need to calculate probabilities, but I don't know what the population is. So I can say, okay, let us assume that the population is normally distributed with mean 30 and variance 25. So this is then part of my model, and then I say, okay, if this is the population and I make a draw from this population, then this is what I expect to see, and then I look at my draws and I match this to the predictions that come from this model, and if these are close, then I say, okay, my null hypothesis about the population is not rejected by the data. This is very important. This is the distinction between failure to reject and accept, which very few people understand. So I took a random variable. I took a random person out of Japan, and I said, let us assume that the population of Japan, the ages of the population of Japan are normally distributed with mean 30 and variance 25. And then I looked at my population, and looked at my random draws, and most of them were within 30 plus or minus 10. That's 2 standard deviations. If you have a 5 standard deviation, which leads to a variance of 25. So if all of the people I drew were within, let's say 20 to 40 age, then I say, oh, my model is working well, because everybody is coming on within the central 95% of the distribution, so my model is good. If I make 100 draws and out of these 95 people are within 20 to 40, I say I have a good model. My sample does not reject the null hypothesis. It does not mean that the ages are actually normal in the population. Right? This is a very crucial distinction. Most people think that when you fail to reject the null hypothesis, it means the null hypothesis is true. But that's not the case. The null hypothesis was just an assumption that we made about the population, and then when we used it, we found that it doesn't conflict violently with the facts. So if we cautiously proceed with using this model, maybe we'll not get catastrophically bad results. This is all you can say. So here are these different types of normal densities. Can someone tell me which color is the density? Oh, acha, it's already written on the graph. All right, so tell me which of these densities has the smallest sigma squared? No, 0. The blue one, yes, it has 0.2. And what is the feature of the graph that shows that this has smallest sigma squared? What do we see in the graph that tells us that this has the smallest variance? It is narrow. It is the narrowest of all the 4 graphs. Which has the highest, just look at the colors, don't look at the legend. Which has the highest variance? Yellow, because it is the flattest. Which one has non-zero mean? The green one, yes. Okay. So the graph tells us information without having the numbers. Now what we want to do, the goal of this lecture is to explain that what happens when you sample from these. So if you sample from the red distribution, what kind of a sample will it be? If you sample from the blue distribution, what kind of a sample will you get? This is basic question of probability. I tell you what the distribution is, you tell me what the sample is like. And so this is what we are trying to explain in this lecture. And the reverse question is, I give you a sample and you tell me what the distribution is like. So these are 4 normal distributions, and one should be able to understand by looking at these distributions or calculation that if I draw an IID sample from the blue density, what kind of numbers would I get? So for example, suppose I drew a sample from the blue distribution and drew one from the green distribution. How would you tell them apart? I have 100 numbers in one column from the blue distribution, 100 numbers IID from the green distribution. What would you look at to tell which one is green and which one is blue? If you look at the mean, that would tell you to calculate the mean of the first sample, and it would be around 0, and you calculate the mean of the second sample, it would be around -2. So that would tell us that this is the green distribution. Oh, this is the same. Okay, here's the uniform density. It is flat between A and B. This means that all numbers between A and B are equally likely, and outside these they have 0 likelihood. So if I was trying, suppose that this A and B, consider this and consider the previous distribution, which is normal. The red distribution is normal 0, 1. Okay, so suppose I had normal 0, 1 and I had another distribution which is uniform from -2 to +2, which is roughly the range of the 95% central range. And I have one column which has numbers from the uniform -2 to, and the other which is normal. What would I look at to find out which one is which? I have 100 numbers from the normal density and 100 numbers from the uniform from -2 to 2. What would I look at in these numbers to try to tell? Yeah?
Same probability of uniform distribution.
What?
With same probability. -2 to 2.
Same
probability. All.
The probability is not seen in the chart. Probability is hidden. It's unavailable. You just have a sequence of numbers. I can do this. Okay, we will do this soon. Here is the Cauchy density. It has its own parameters. Here is the Kumaraswamy distribution, which has many different types of shapes. This is the beta density for different parameters. It takes many different shapes. Okay, there are some lectures. Okay, now I'm going to switch to the Excel mode and alright, so what I am going to do, number of variables is 100. Oh, sorry, just one. Number of random numbers is 100. Or let's just make it much smaller. Let's make it 20. Okay, I'm going to make this normal distribution. Range 0, 1. Output range 1. Okay. So here are 20 normal numbers, and let's do another column of uniform numbers. Okay, here's uniform, and between -2 and 2, and I want to make the output in B1. Okay, so now because I'm doing this in front of you, you know that the second one is uniform and the first one is normal. But now suppose that you have these two numbers. I have given this to you as a exam, and now you tell me what is it that tells you that the second one is uniform and the first one is normal. Now it's quite hard to see, but there must be something that tells us. I'm going to reduce the decimals. That will make it easier to see what's happening. Okay, just one decimal place is enough. So first of all, if we take the mean, both will have mean 0 because the theoretical distribution means 0. So that's not going to help us. Standard deviation, we can try to look at that. Let's look at equals STDEV of okay, standard deviation was 1.13. It's theoretically supposed to be equal to 1. So by random fluctuation, and this is 1.25, not much different, slightly higher. Actually, standard deviation of the normal is higher. It's around 1.25 and the normal is around 1, if I remember correctly. So not very helpful. क्या हुआ? कैसे ग्राफ करें? कैसे प्लॉट बनाए? हिस्टोग्राम बनाए. Histogram is a good idea. We can do a little bit better than that. You see, let's make one of the things I can do is sort them. This is a useful thing. sorting helps. Let me get rid of the standard deviation. Sorts में problem हो जाएगी. Alright, so I'm going to sort these. That way makes it easy to make the histogram. Sort smallest to largest. Don't expand the selection, just do this one. Continue with the selection. Alright. Now, well, one of the things that's cheating but very easy to do is to look at minus 2.2 and say, of course, this must be normal because the uniform is only between minus 2 and 2. But suppose that that's not allowed. It's sort of too easy. Now, we can look at the histogram mein. If I look at the range from minus 2 to minus 1, and in the uniform distribution, divide it into 4 parts: minus 2 to minus 1, minus 1 to 0, 0 to 1, and 1 to 2. So there are 4 parts. All 4 of them should have equal numbers. But in the normal, the 2 end points should have fewer numbers and the center should have more numbers. So that's one way to look at it. So let's look at the first 5 numbers. In the uniform distribution, this should go from minus 2 to minus 1, and that's what is happening. But in the normal distribution, this is further away. Actually, this is worse in the sense that you have 7 numbers in the range from minus 1 to 0, contrary to what our prediction would be. Our prediction would be that the normal distribution will have fewer numbers in this range from minus 1 to 0, but it actually has more numbers in this range. It's just a random fluctuation. Now between minus 1 and plus 1, and in the last range we have between 1 and 2, I have here 4 numbers and 5 numbers. It's not easy to tell between these two. On these tests, I'm not sure that we can find out. Sometimes it is true, and if the sample size is quite small, and it may not be possible to distinguish between them very cleanly. If I go to a sample size of 100, it becomes very easy. There is a concept, a theoretical concept, which is called the what? Law of large numbers. There is something which is called the Kullback-Leibler distance or information. This gives you the distance between two densities. And if the two distributions have a large distance between them, then it becomes easy to differentiate with them for small samples. For example, if I have a normal 0,1 and a normal 0,1.1, then it will take a huge sample to tell them apart. If I have a normal 0,1 and a normal 0,2, I can tell them apart with fairly small sample. So here, these two distributions are not all that distinct. If I made the samples larger, I would be able to tell them apart, perhaps. So, law of large numbers is involved. It is important. It is useful in the sense that if let's look at the law of large numbers here. And let me use this to make a prediction. Okay, so let's look at equals CDFN. अच्छा ये CDFN नहीं allowed है. नॉर्मडिस्ट है. अच्छा, नॉर्मडिस्ट, यस, नॉर्मडिस्ट सही है. नॉर्मडिस्ट ऑफ -1. ओ, नॉर्म एस डिस्क करना था, सही है. Okay, so normdist is 15.8%. So the about 15.8% of the sample should be less than -1, right? This is the probability that x is less than -1. As opposed to this, for the uniform distribution, the probability of being in the range below -1 is how much? 25%, exactly. So let me just to explain this a little bit further. Let me try the following experiment. -2 minus 1.9 . Alright, now equals norm S dist of this thing okay. So these are how the probabilities change with the this is the normal probabilities of being below that value. I am going to put down here the uniform probabilities. So this is going to be equal to it's 0.1 divided by 0.1 divided by 4 is the base, right? 4 is the total range, and this interval has 0.1 in it, so I can take this divided by 4, that's 0.025. What happened here? Acha. That's not how it works. Okay, so ठीक है, मैं करता हूँ इसको सही. क्या हुआ? ओ अच्छा, I see. Right. नहीं, ऐसा भी नहीं हुआ. अच्छा, इक्वल है इसमें, सही है. Now this works. Thank you. I didn't know about this. Okay, ऐसा इतना sensitive है. Well, ये Excel. अच्छा, so you see, ये मैंने इसलिए किया कि I want to look at the place where there is the maximum discrepancy, क्योंकि that is going to be the easiest to detect. So what I want to do here is to just look at the differences. This minus this. यहाँ पे 2% डिफरेंस है. 3, 0, 1, 0, 3, 0, 4, 0, 5. ये 7%, यहाँ पे 8%. Basically, the maximum difference already occurs at -1. राइट, जो यूनिफॉर्म डिस्ट्रीब्यूशन और नॉर्मल डिस्ट्रीब्यूशन में जो मैक्सिमम डिफरेंस है इन प्रोबेबिलिटीज. तो दिस इज द राइट इंटरवल टू लुक एट. वो हमने ऑटोमेटिकली फर्स्ट क्वार्टर लिया था जस्ट बिकॉज इट वॉज कन्वीनियंट, बट actually that is the best. If you are going to look at only one bin within a histogram, then this is the best bin to look at. So in this bin, the normal distribution will come out 15.8% of the time, and the uniform will be there 25% of the time. So now we want to look at the how many. So I have taken a sample of 20 numbers from a normal distribution, और उसमें से we found that 7 of them were in this interval, right? So actually what I want to do is to find out that what is the probability of, okay, let's look at just the simplest thing is to look at the probabilities. So equals binom dist. अच्छा, इसको मैं पहले skip. I want to do 1 2 3 4 0 1. Right, now what I want to look at is what is how many numbers, how many normal numbers will we find in this bin which is going from minus infinity to minus 1. So every number falls in this bin with probability 15.8%. So and this is a trial. This is and we have a sequence of binomial trials. Every time I make a random draw, it has a chance 15.8% of ending up below minus 1 and a chance 84.2% of being above minus 1. See? One normal random variable. What is the probability that it's less than minus 1? नहीं समझ में आ रहा? Yeah? What is the probability that a normal random variable is below minus 1? What is it? 15.8%. That's what the normal distribution tells us. So we will count a normal variable as being, we'll count it if it is below minus 1 and we will not count it if it is above. Okay? I'm just counting the number of variables which are coming out below minus 1. Okay? So the probability of getting a 1 and the probability of probability of sitting in this box which is going from minus infinity to minus 1 is 15.8%. Okay? So what is the probability that none of the random variables is below minus 1? 20 variables हैं हमारे total. What is the probability that there is 0 in this box? Yeah, 85.2% raised to the power 20. ठीक है ना? One variable chance is 85% and all of them is 85 to the 20. So this is going to be equal to binom dist parentheses. Now the number of trials, number of trials is 20, comma, probability is 15.8%. I want to write this as 0.158. Oh, no, that's not. पहले नंबर ऐसा है, सही है. तो पहले तो हम लोग ये नंबर ये डालें, ये 0, कॉमा, उसके बाद 20, उसके बाद 0.158 comma, do you want to keep it cumulative? Alright, let's put it cumulative. So 1. Alright, now checkbox. So 3%. Alright, so the chances of getting 0 in less is about 3%. Chances of getting 0 or 1 is 15%. Chance of getting 0, 1 or 2 is 3.6%. 0, 1, 2 or 3 is 60%, and so on.
This is chances of getting 3 numbers less than
minus 1, exactly,
-1.
from a normal. You have to keep track of this, what we are doing here. Now, I want to compare this to the uniform probabilities. So, what is the uniform probability that none of them will be here? That's going to be equal to parentheses 0.75 raised to the power of क्या रखा है ये? नहीं, that's star. 6. अच्छा, कौन ये बतला है? वाह. So ये कौन सा पावर होगा? 20, exactly. So 003, यानी this is क्या हुआ?
Weird. I mean,
हाँ?
like chances of getting 12 or 13 numbers less than -1 is coming to be 100%.
That's right. यानी अच्छा.
ये increase हो रही है. Doesn't make sense. कम होनी चाहिए.
You are right.
Because
क्या है?
15% chance of getting 1.
There's something wrong here. This is wrong. It can't be. चलो probability देख लेते हैं, मगर why is it, यानी maybe this something wrong, but anyway इसको 0 कर लेते हैं तो देखते हैं फिर क्या होता है. Alright, this seems better. Alright, so I'm going to also calculate this by the binomial method. Equals binom dist, brackets, number of trials should be the same, 0, comma, 20 is the total. And now what is the success probability with a uniform distribution? 0.25. That is the probability that a uniform will be less than -1. समझ में आ रही है? नहीं समझ में आ रही. You're completely lost. चलो, तुम इसको समझा सकती हो? तुम्हें भी नहीं समझ में आ रही. It is not difficult. समझ में आ रही है? तो ये बाइनोमियल वेरिएबल है. 20 अच्छा K1 20, तो ये अगली चीज में क्या लिखूं यहाँ पे? 0.25 और 0 लिख देते हैं.
So what cumulative was saying was chances of getting 1 or 2 or 3 or 4. It was adding.
अच्छा, वो ऊपर से जा रहा था. सही. वो रिवर्स कर दिया था उसने. लेस देन इक्वल टू के बजाय ग्रेटर देन इक्वल टू. It actually goes towards the center. I think that's what happens. All right. So here you have it. तो actually जो हमने देखा, that was 7. That only had a 2% probability. See, generally speaking, जो हमारी high probability event है वो ये है कि 0, 1, 2, 3 या 4 तक आ जाएगा. एक्चुअली हाँ, let me do that now. Summation जो हम cumulative चाह रहे थे for a reason. I wanted to show you something. सही है, ठीक है. ये मैं पहले कॉलम का क्यूमुलेटिव्स बनाने की कोशिश कर रहा हूँ. ओके, दैट्स द क्यूमुलेटिव्स फॉर द नॉर्मल. सो बाय द वे, डज एवरीबडी अंडरस्टैंड ऑल ऑफ दीज नंबर्स? यानी दिस इज वेरी इंपॉर्टेंट, क्योंकि ये हम लोग बहुत ही ओके ये तो हमने प्रोबेबिलिटी डाल दी यहाँ की. दिस इज द प्रोबेबिलिटी. उसके बाद अब हम ये कहेंगे कि इक्वल्स this plus this. तो अब ये क्यूमुलेटिव बन गया, ठीक है ना. एंड नाउ दिस विल गो क्यूमुलेटिव. इसी तरह से हम इसको भी कॉपी कर सकते हैं टू द नेक्स्ट कॉलम. क्या हुआ? ओ अच्छा, हमने वो नहीं किया. इक्वल्स, अच्छा पूरे कॉलम को कॉपी करना था. दिस प्लस दिस. So basically, we expect to see. Sorry, skip करना मुझे. What I want to show you, what I want to explain to you is what are the chances of success if we follow the rule कि whichever distribution, I have two columns, remember, whichever column has less numbers in the 0 to 5 range, that is the column I will say is the normal distribution. So that is a decision rule. That is a way of telling. Now in this particular case, I will go wrong. I will make, if this is my decision rule, I will take the normal and I will say that this is the uniform and the other one will be the, according to me, the normal. This is because all probabilistic procedures have a chance of mistake. The only thing we can do is to calculate how much is the chance of this mistake. And that's what I was trying to do with these calculations. So, this is going to be a bit complicated, but basically what we want to do is to say that the chance of the uniform variable having 0 observations in the range. I'm going to decide that this is uniform if there are more observations in the -2 to -1 range. So 0 pe to I will not decide that this is uniform. So let's start with 1. So there's a 2% chance, 2.4% chance that the uniform will give me 1 observation, and in that case, if that happens, then there is a 3% chance that the probability that the normal will be even less, and there's a 97% chance that the normal will be the same or higher. So if it is the same, I will not make a mistake, I will not know what to do. But if it is higher, I will make a mistake. So suppose I want to calculate what is the chance of making a mistake. So it will be 0.24 times 0.36, the cumulative, exactly. Then there is a 36, नहीं, इन दोनों को add करना चाहिए. Alright. So 2% times 36 plus sorry, पिछले वाले पे चले जाते हैं 21. This cumulative is the wrong one. So 2.4% times 21% plus 24% plus 19%. There is a pretty good chance in this case, क्योंकि the uniform came out very low, so the chances that the normal will come out better is pretty high. So chances of my making a mistake are very high.
So for these two samples, if we plot kernel density curves, would that help us?
No, not at all. Kernel density is the reverse problem. That, oh acha, you would say that's a visual test. You could try to plot what is the kernel density. That's take the IID sample and try to plot what is the density. Now actually, if you try to do this, you will find that a sample of size 20 is too small. You don't get very reliable estimates of your density, so you will get very poor estimates.
Uniform might be flatter than.
Exactly. You can look, and just like we made it, so with 20s, chances of your making an error are quite large, and that is what I was trying to quantify. What is the chance of making an error? And you can do that, but it's a complicated calculation. Now if we go up to 100, then the chances of our making a correct decision become very strong. So I can actually show how that works by looking at the following number. That would have been easier, less complicated than what I did. Let's look at 20. No, it's not easy. All right. Yeah. Okay, I got an idea. $40, $60, $80, $100. Right, so these are the sample sizes that I am looking at. I am looking at the uniform probabilities. So I expect to see about 1/4 of the sample below below -1. I'm going to extend this a little bit and say that the distribution is uniform if it is close to 1/4. So I can just say that this is binom dist of. Now what is close to 1/4? Well, 5 is the number that I would look at as exactly the quarter. Now I want to look at what is the SD. The SD is NP1 minus P, right? Is that the variance? Square root NP1 minus P. So N is 20. So let me do that calculation. Okay. N is 20. P is 25%. 1 minus P is 75%. So it's कितना हो गया? 20 times 1/4 times 3/4 is 5 times 3, 15 divided by 4, right? 15 divided by 4 is approximately 4, right? That's the 3.75. That's NP1 minus P, and इसका square root लेना पड़ेगा, तो square root of 4 is around 2. Alright, so the number of trials that I want to look at is 7. Yani 5 is your expected number, and I go up one standard deviation to say that if the number of heads, if the number of times that the distribution is below -1 is 7 or less, I will decide that this is uniform. Okay, so 7 comma, now the number of trials is 20, which I want to take from here, comma 0.25 comma do I want cumulative? Yes, I want cumulative. Oh, ये फिर उल्टा कर देगा इसको. अच्छा. All right. So what I am going to do is put 1 minus this here. Okay. It's only a 10% probability that the number will be 7 or less. That doesn't sound right. The other numbers seem right, but this one doesn't. So, oh, acha, but that's very strange. ये गलत है, सारा गलत है ये. Alright, so I think we are running out of time, and basically what we can do is you can calculate for a given bin what is the probability that यानी given a bin you can calculate कि इसमें कितने numbers आएंगे. So approximately it will be 1/4 of whatever. So if you have 100, then the number in the bin will be about 25, and the SD will be about 5, I think. So it will be. So you can say that the number that you will see will be between 20 and 30 for a uniform distribution. For a normal distribution, it's 15.8, 16%. So you will expect to see 16, and you will expect to see between 11 and 21. So now at 100, the chances of your making a mistake are fairly low. Because 21 आ सकता है. There is some probability. If it get 21, then you will be confused. It could be from normal or it could be from uniform. But if the number comes out between 11 and 20, you are pretty sure that it's normal. If it's between 21 and 30, you're pretty sure that it's uniform. But even then, there will be some probability of error. It will be maybe 5%, it will be maybe 2%. You can calculate all of these numbers. So that was the main lecture. That now we have understood at the end of this lecture what is a distribution, what is an IID sequence, and how does the IID sequence reflect the distribution by taking any particular bin and calculating according to the parent distribution what is the probability of being inside that bin. And then you have a binomial distribution which tells you, and given two different distributions with different probabilities, you can discriminate with them if you have a sufficiently large sample size.
So इसमें जो IID की फंक्शन थी,
क्या थी?
IID identically distributed, ये without replacement से effect हो जाती?
Without replacement, though it is not technically valid. Magar, if the sample size is very large, then it makes no difference. Yani the error made by replacing with replacement and without replacement is small. If you have a sample of size 1000 and you make 10 draws from it, then with replacement, without replacement, it will be pretty much the same. But if it is sample is if your population is 100 and you make 10 draws, then now it is more risky, and the approximation will not be as good.